Welcome to Outbreak Brief, the podcast that takes you inside the world's most dangerous infection.
Glad to be here.
So today, for this deep dive, we are tracking something that I would call an invisible aquatic assassin.
That is actually a perfect way to describe it.
Right, because it doesn't, hunt in a jungle. It doesn't lurk in exotic wildlife. It actually hides right in plain sight.
Deep inside the plumbing.
Exactly. Deep inside the water systems we rely on every single day. We're looking at a microscopic killer that, it essentially turns our modern conveniences, the very things that make our buildings comfortable and our hospitals functional, into potential threats.
Yeah, it's a pathogen that really exploits human engineering.
It does. And today we are heading into the dark, watery corners where this pathogen thrives. We're going to break down exactly what it is, where it came from, and why you might want to rethink that next hotel shower.
Yeah, to really understand the sheer panic this pathogen can cause, we actually need to go back a few decades.
Let's do it. Where are we starting?
We need to go back to July 1976. The setting is Philadelphia. That's the bicentennial year, so the city is just packed. And the American Legion, which is an organization of U.S. military veterans, they're hosting this massive convention at the Bellevue Stratford Hotel.
All right, I've seen pictures of those huge crowds.
Huge. Over 2,000 attendees are gathered. It's festive, it's crowded, it's a celebration. But within days of the convention wrapping up, something goes terribly wrong.
People start getting sick.
Very sick. A mysterious and just incredibly severe respiratory illness begins tearing through the veterans. And not just the ones who stayed at the hotel, but even people who just visited it for a few hours.
Wow. The suddenness of it must have just terrified public health officials. I mean, 2,000 people scatter back to their homes across the state, and suddenly they are dropping ill with massive lung failure.
It was a massive crisis. I mean, the CDC literally deployed an army of epidemiologists to Pennsylvania.
Because they had no idea what it was?
None. Ultimately, 182 people were infected in that initial cluster, and 29 of them died.
Oh my God, 29 people.
Yeah. And the most terrifying part for the investigators was the total lack of a transmission vector.
Right, because usually you look for, like, the potato salad at the buffet.
Exactly. But it wasn't food poisoning for the banquet. And it wasn't spreading person to person. It wasn't from handshakes or sharing drinks or coughing on each other.
It's like a locked room mystery. If it's not the food and it's not each other, what is it?
They finally realized the invisible killer was circulating in the very air the veterans were breathing. It was being aerosolized by the Bellevue Stratford's own air conditioning system.
Wait, the AC was blowing it into the rooms?
Close. Specifically, it was the cooling towers up on the hotel roof. They were raining down this invisible contaminated mist right onto the sidewalks and directly into the building's ventilation intake.
That is a terrifying scenario.
Yeah.
Because you can't fight what you can't see. And I mean, you obviously can't just stop breathing.
Right.
So when those investigators finally isolated what was in that cooling tower mist, what exactly were they looking at?
They discovered a completely new bacterium. They named it Legionella pneumophila. In infamy of that American Legion outbreak.
Legionella. So it literally gets its name from the victims.
Exactly. And under a microscope, it's a rod-shaped bacteria. It is aerobic, meaning it requires oxygen to survive, and it is gram-negative.
Okay, so gram-negative. For those who aren't microbiology majors, what does that mean for us?
Well, a gram-negative bacterium has a thin cell wall, but, and this is the key part, it is sandwiched between two lipid membranes.
So it has extra layers.
Yeah, that outer membrane acts like a microscopic suit of armor. It makes it incredibly resilient against certain environmental threats.
So it's tough to kill.
Very. And when it infects a human, it causes a disease with two very distinct faces.
Two faces, like different symptoms entirely.
Yeah. One is called Pontiac fever, which is a relatively mild, self-limiting illness. It basically feels like the flu, but it never progresses to pneumonia.
Okay, so that's the good face, if you can call it that.
Right. The other face is Legionnaires' disease. And this is a severe, rapidly progressing atypical pneumonia. It can very quickly lead to respiratory failure, shock, and multi-organ dysfunction.
But wait, if it's just a bacteria, right? Why does it trigger such a severe respiratory failure compared to just like a standard chest infection?
It all comes down to where it hides. Because Legionella is an intracellular bacillus.
Meaning it goes inside our cells.
Exactly. It doesn't just float around in the lung tissue or the bloodstream. When you inhale those contaminated water droplets, the bacteria travels deep into your lungs, and it is immediately met by alveolar macrophages.
The macrophages, those are They're like the immune system's cleanup crew, right?
They are the apex predators of your immune system. They're supposed to swallow up invading bacteria, hit them with digestive enzymes, and absolutely destroy them.
But I'm guessing Legionella doesn't just let that happen.
No, it actually survives inside the macrophage. It injects specific proteins that block the macrophage from digesting it. Then, it hijacks the host cell, feeds off its nutrients, and turns that immune cell into its own private replication factory.
It's literally like a burglar breaking into a police station, right?
All right.
Then locking the doors from the inside and using the station as a hideout to plan their next heist.
That is exactly what it does. The very cells designed to protect us become the incubators.
That is so sinister.
And eventually, that macrophage just bursts open, releasing thousands of new bacteria to infect the neighboring cells.
Oh, wow.
Yeah. And the discovery of this mechanism following that 1976 outbreak, it was a massive paradigm shift. It forced the medical community to realize we had a deadly blind spot. But it's crucial to know that Legionella is not some lab-created monster.
Right.
And it didn't just magically appear in 1976. It is completely natural environmental bacteria. It has existed for millennia in soils, rivers, lakes, and ponds all over the world.
Wait, hold on. If it has been in rivers and ponds for thousands of years, why did it suddenly become a headline-grabbing lethal threat in the modern era? Why 1976?
Because, as human civilization advanced, we essentially built luxury resorts for this bacteria.
What do you mean luxury resorts?
Well, as we developed complex artificial water systems, I'm talking large-scale plumbing, cooling towers, massive hot water tanks, and high-rises, we inadvertently created the absolute perfect conditions for Legionella to thrive.
Because it likes that environment better than a cold river.
Right. They love warm, stagnant water. Out in a natural river, they are just a minor part of the ecosystem. But inside man-made plumbing, they form what are called biofilms.
Biofilms. That's
Yeah.
like the slime you feel on the inside of an old pipe, right?
Exactly. They are thick, slimy, protective layers of microorganisms that adhere to the insides of pipes. And once Legionella embeds itself deep inside a biofilm, that slime acts as a shield. It protects the bacteria against extreme temperature changes and even standard chemical disinfectants like chlorine.
So we basically engineered the perfect safe environments for it to multiply,
We really did.
which I guess brings up the actual transmission. If it's in our pipes, how does it get from the pipe into our lungs? Because there are a lot of misconceptions about how people actually catch this.
Oh, definitely.
Yeah.
So let's clear those up right now. Legionnaire's disease is not spread person to person.
Okay.
You don't catch it from someone coughing on you in an elevator.
Yeah.
There is also no zoonotic transmission, meaning it does not jump from animals or pets to humans.
Good to know. So it's all about the water.
Yes, it spreads primarily through the inhalation of contaminated water aerosols. Think of literally any device that creates a fine mist. Or, in some cases, particularly in hospital settings, it spreads through microaspiration.
Microaspiration, like choking on water.
Sort of. That is when tiny amounts of contaminated drinking water or saliva accidentally slip past the vocal cords and go down the wrong pipe into the lungs.
Yikes.
And once a person is exposed, whether through a mist or microaspiration, the incubation period is typically 2 to 10 days.
2 to 10 days. And when you think about an average daily routine, I mean, you take a shower where the shower head creates a mist.
Right.
You walk past a decorative fountain in a lobby, or you spray the windshield wiper fluid in your car. I mean, Legionella has been recovered from all of those places, hasn't it?
It absolutely has.
Yeah.
In fact, the windshield wiper fluid tank of a car can be a massive breeding ground.
Wait, really? Your car?
Yeah. If it's filled with just regular tap water instead of genuine washer fluid, it's a huge risk.
Yeah.
Because the engine heat keeps that water perfectly warm for the bacteria.
That is crazy. I know so many people who just use a hose to fill that tank in the summer.
It's a terrible idea.
Yeah.
But here is an even more fascinating geographical plot twist for you.
Oh, I love a plot twist.
While Legionella pneumophila dominates in North America and Europe via those water systems, if you go to New Zealand or parts of Australia, a totally different species called Legionella longbeechae is the primary culprit.
Oh, okay.
And the transmission medium is completely different. People aren't inhaling water vapor from a cooling tower down there.
What are they inhaling?
They are inhaling contaminated dust from bagged gardening potting mix.
Potting soil. Wait, how does an aquatic bacteria thrive in a bag of dirt?
Well, bagged compost and potting soil actually retain a really high level of moisture.
Oh, right.
Yeah. So inside a sealed plastic bag sitting in the sun, it acts like a humid, warm greenhouse. The bacteria just thrives in that damp organic matter. So when a gardener rips open the bag or, dumps it into a planter, a dry cloud of dust and vapor hits their face.
And they inhale the bacteria directly.
Exactly.
Okay, but this raises a huge question for me. If this bacteria is in our showers, our fountains, our cooling towers, and, our potting soil, why aren't we all constantly developing severe pneumonia? I mean, shouldn't everyone be sick?
That's a great question. Thankfully, a healthy human immune system is generally very good at clearing the exposure.
Because of the initial physical barriers?
Yes, the barriers in our respiratory tract and a robust cellular response usually stop it before the bacteria can hijack enough of those macrophages. The severe outcomes of Legionnaire's disease are highly, highly targeted.
So who exactly is most at risk here?
Vulnerable populations include males, individuals over the age of 50, and current or former smokers.
Why smokers specifically?
Because smoking damages the cilia. Those are the tiny hairs in the lungs that naturally sweep out debris and bacteria. But the highest risk falls on those with underlying conditions. So chronic lung disease, diabetes, iron overload, or anyone who is pharmacologically immunosuppressed.
Like cancer patients or transplant recipients.
And
that targeted vulnerability, that's what makes this pathogen exceptionally devastating in healthcare settings, isn't it?
it is a nightmare in healthcare settings.
I was looking at the data, and it shows that 19% of outbreaks occur in long-term care facilities, and 15% occur in hospitals.
Yeah.
It literally preys on the already sick. I mean, getting Legionnaire's disease out in the community is dangerous, but healthcare-associated pneumonia caused by Legionella is a completely different beast.
It really is. It usually occurs in clusters, reflecting a point source exposure, like a contaminated hospital water supply or even medical equipment.
Wait, medical equipment?
Yes, like respiratory ventilators that were improperly rinsed with tap water instead of sterile water.
Oh, that is tragic, because you're literally forcing the mist straight into a vulnerable patient's lungs.
And the mortality data heavily reflects that tragedy. A hospital-acquired infection carries a significantly higher risk of death. These patients already have multiple comorbidities, their immune systems are compromised, and the infection can progress with terrifying speed.
So what does that progression actually feel like for the patient? If someone inhales that mist, what are the early warning signs? Does it hit them all at once?
It starts deceptively.
Yeah.
Usually 2 to 10 days post-exposure, the patient develops a gradual onset of fever, chills, severe malaise, and myalgia, which are intense muscle aches.
So it basically feels exactly like a bad case of the flu.
Exactly. But it rapidly devolves. As the bacteria multiplies inside those macrophages, it triggers an intense inflammatory response.
Yeah.
And that severely damages the alveolar and capillary structures in the lungs.
So breathing becomes really difficult.
Very. The patient develops a dry, hacking cough, severe shortness of breath, and pleuritic chest pain.
Pleuritic chest pain, that's that sharp stabbing pain every time they try to take a deep breath, right?
Yes. But the crazy thing is it doesn't stay confined to the lungs.
It spreads.
Well, it causes bizarre extrapulmonary symptoms. And this makes it incredibly difficult for a doctor to diagnose purely based on clinical presentation.
Because it doesn't just look like pneumonia anymore.
Right. Patients often present with severe gastrointestinal issues, watery diarrhea, nausea, vomiting, abdominal pain, and then there's the neurological chaos.
Neurological? Like what?
They can experience severe confusion, splitting headaches, and even cerebellar ataxia.
Cerebellar ataxia. That's like a sudden loss of muscle coordination, right?
Exactly. They lose their balance. Pathologically, the body is undergoing massive systemic stress. In fact, doctors actually look for a classic diagnostic clue called relative bradycardia.
What is that?
Normally, when a human body has a raging high fever, the heart rate speeds up significantly to pump blood and cool the body down. But in many Legionnaire's cases, the patient has a high fever, yet strangely, their heart rate remains relatively slow.
That is so weird. Why does that happen?
It's a sign that the body's normal regulatory systems are failing. Inside, the body's throwing absolutely everything it has at the infection. There is an initial hyperinflammatory phase, a massive cytokine storm.
Right.
But eventually that storm causes what we call immunoparalysis.
Immunoparalysis, that sounds exactly as bad as I think it is.
It's terrible. The immune cells literally exhaust themselves, they downregulate their receptors, and they lose the capacity to respond to any further stimulation. The body just stops fighting.
Wow. But if the bacteria is hiding inside our own immune cells and the entire immune system is paralyzed, how does a doctor fight it? I'd imagine standard antibiotics like penicillin don't work well since they generally target the bacterial cell walls floating freely in the bloodstream.
You're exactly right. Standard beta-lactam antibiotics like penicillin completely fail against Legionella.
Because the bacteria is sheltered deep inside the macrophage.
Exactly. It's hiding behind the human cell wall. So you need specific intracellular penetrating antibiotics. The drugs have to be able to cross the human cell membrane and attack the bacteria inside its hideout.
So what are the options?
The gold standard treatments are macrolides, like azithromycin, or fluoroquinolones, like levofloxacin, and it is not a quick fix. It usually requires a 7 to 21-day course of heavy treatment, sometimes even longer for immunocompromised patients or those fighting for their lives in the intensive care unit.
The human cost here is just sobering. I mean, even with those highly specific antibiotics, about 1 in 10 people who contract Legionnaire's disease out in the community will die from complications like lung failure or septic shock.
Yes.
And if the infection is acquired during a stay in a healthcare facility, that mortality rate skyrockets to 1 in 4. Roughly a third of all hospitalized cases end up in the ICU. Lives are absolutely on the line here, and early, accurate diagnosis seems like the only thing standing between recovery and a fatal outcome.
It really is, which is why doctors have to maintain a very, very high index of suspicion. Because the symptoms mimic so many other types of severe pneumonia, a physician has to proactively ask the patient about their recent travel history.
Right, like were you at a hotel?
Yeah. What's your occupation? Have you been in a hot tub recently? Have you had a recent hospital
I
stay?
have to play detective.
But wait, since this is so deadly to the elderly and the immunocompromised, why haven't we developed a vaccine? I mean, we have vaccines for other types of bacterial pneumonia, right?
We do, but we have 0 vaccines available for Legionella. None. Why not?
It comes directly back to those complex virulence mechanisms we just discussed. Because Legionella injects those specialized proteins to hijack the macrophages, and because it induces that profound immunoparalysis, developing long-lasting artificial immunity has proven incredibly difficult.
Because vaccines need the immune system to remember the threat.
Right. To make a vaccine work, you need the immune system to recognize the antigen and create memory T cells and B cells. But Legionella actively suppresses the very cells responsible for that process.
That's incredibly frustrating.
It is. Because we lack a vaccine, we are entirely reliant on fast medical treatment and, much more importantly, environmental prevention.
Okay, let's talk about that. Since we cannot shield the human body with the vaccine, we have to shield our buildings. We have to look at the engineering side of things. How do we actually stop this bacteria from colonizing our plumbing?
It requires rigorous, constant water management. Building owners and facility managers have to implement comprehensive water management programs, and these heavily rely on engineering standards set by organizations like ASHRE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers.
Oh, got it.
This is highly technical work. It means identifying what they call dead legs in the plumbing.
Dead legs. What are those?
They're sections of piping where water stops flowing and just sits stagnant. Maybe it's a pipe leading to a sink that nobody ever uses.
Right.
That allows biofilms to grow.
Okay, so you have to flush those out?
Yes. It also means strict temperature controls, keeping cold water truly cold, and hot water hot enough to kill the bacteria, generally above 140 degrees Fahrenheit. It also means maintaining adequate and constant chemical disinfectant levels throughout every single inch of the building's pipes.
And performing meticulous, regular maintenance of those massive cooling towers, right?
Absolutely.
And regulatory bodies are finally putting some teeth into these engineering standards. I saw that the Centers for Medicare and Medicaid Services, or CMS, issued a highly specific policy mandate.
It did.
They now explicitly expect healthcare facilities, hospitals, and long-term care facilities to actively conduct facility risk assessments. Administrators have to map out their plumbing, identify exactly where Legionella could grow, and implement policies to inhibit that microbial growth.
And it's a huge deal. If a facility cannot demonstrate they have these environmental controls active and monitored, they risk losing their funding or being cited for severe noncompliance.
Which is how it should be, considering the mortality rate. But there is also a strong element of individual prevention for the listener at home, right?
Oh, definitely. If you own a home hot tub, you must maintain it properly. Keep the right chemical balances and constantly check the filters.
And what about the cars?
Right. If you are filling your car's windshield wiper fluid, use genuine washer fluid containing methanol. Methanol kills the bacteria. Don't just use a garden hose. And if you are gardening, especially in places like Australia or New Zealand, where Legionella longbeachae is prevalent, Simply wearing a mask and gloves when handling potting soil is a highly effective way to protect yourself from inhaling that contaminated dust.
Simple steps, but they can save a life.
Yeah.
But looking at the global data, are these engineering controls and regulations actually working? Are we driving the numbers down?
Surprisingly, no.
Really?
The global incidence is actually rising sharply. In the United States alone, between the years 2000 and 2014, reported cases surged by an astonishing 286%.
286%? That's massive.
It reached around 5,000 reported cases in 2014. And epidemiologists widely agree that because the disease mimics other typical pneumonias, it remains vastly underdiagnosed.
So the real number is probably way higher.
Oh, absolutely. A recent systematic review looking at antibodies in the general population found that about 13.7% of people have been exposed to it at some point in their lives.
Wow.
We also see a very strong seasonal correlation. Outbreaks spike heavily with higher summer temperatures and heavy rainfall.
Because the rain splashes it up?
Yes, the rain splashes the bacteria from the soil into the air, or it washes massive amounts of the bacteria into the municipal water reservoirs that eventually feed our buildings.
A 286% increase over just 14 years is a massive red flag. What are the biggest remaining unknowns? Where is the medical research focused right now to try and get ahead of this?
The single major bottleneck we are facing right now is diagnostics.
Diagnosing it quickly enough.
Exactly. Right now, hospitals rely heavily on a rapid urine antigen test. It has a fast turnaround time. You get results in hours. But it has a critical flaw. It only detects Legionella pneumophila serogroup 1.
But there are other serogroups, right?
Yes, while serogroup 1 is the most common cause, there are over 70 serogroups and 60 species of Legionella. If a patient is infected with a different serogroup, the rapid test comes back negative.
And then they might not get the right antibiotics in time.
Precisely. Culturing the bacteria from a patient's sputum remains the gold standard, but it takes days to grow and requires specialized laboratory media.
What about PCR testing? We do that for viruses.
We can use PCR testing, which looks for the bacterial DNA and is really accurate. But it requires expensive equipment that many rural or smaller hospitals just don't have. We desperately need faster, comprehensive bedside diagnostics.
Yeah, that makes sense. As we look at the rising case numbers, there is a paradox I want to leave you with, to everyone listening. We know this pathogen thrives in stagnant, warm water. But as a society, we are pushing to design more environmentally conscious green buildings to conserve our water supply.
Right.
We install low-flow faucets, rainwater catchment systems, high-efficiency plumbing. But by doing so, we are drastically increasing what engineers call water age. Because the water flows so slowly, it sits inside the pipes for days instead of hours. The protective chlorine dissipates. The water slowly warms up to room temperature.
It's a perfect storm.
By trying to save the planet's water, are we inadvertently engineering the ultimate breeding ground for this aquatic assassin? It's terrifying to think that our modern quest for environmental sustainability might be creating thousands of microscopic Bellevue Stratford hotels hidden right inside our very walls. Stay informed. Stay prepared. This has been Outbreak Brief.